Hello and good morning, everyone. My name is Adab Mahmood. I'm a graduate student at the University of Toledo, and today I'll be presenting the paper titled A GaN-based 4-switch buck boost converter using ripple correlation control for maximum power point tracking in dynamic deep space environments. So for this paper we have worked in collaboration with Jet Propulsion Laboratory, NASA JPL. So let's begin. This is the brief outline of the whole paper, where I'll start with an introduction on the paper and then talk about the maximum power point tracking algorithm that was used, which is the ripple correlation control, or RCC, and then talk about the buck boost converter prototype that was developed for this project, and next move on to the simulation of the whole system in SaberRD, and then finish up by some concluding remarks and points on future work. So let us go ahead with the introduction. So as we know that solar energy is now a major contributor of power in most spacecraft, and due to the higher computational and instrumentational needs of the spacecraft, we need to make sure that the power converters equipped in the spacecraft always maintain a high power efficiency, and along with that we need to make sure that the power converters also have high power density because of the mass and volume constraints for designing the spacecraft. So here we see a chart showing the maximum power point from a PV cell that was recorded during a geosynchronous Earth orbit cycle. And at 2 points that I have highlighted here, we see that there are rapid changes in the maximum power point. So because these two changes are because of the shift in the solar irradiation on the PV array of the spacecraft, and we need to make sure that this maximum power point is always being tracked by the power converter so that we get the maximum power out and have the power converter work at its maximum efficiency. Now let's talk about the algorithm that was used for tracking the maximum power point. Here I've shown the MPPT system block diagram, where we have the PV array connected to the DC to DC converter, where it is being controlled by an MPPT controller. The MPPT controller is in a closed loop system here, where it is getting feedback from the PV array and the DC to DC converter in terms of PV current, PV voltage, and the inductor current from the DC to DC converter, and is controlling the converter by providing it with a duty ratio which is corresponding to the maximum power point. Here we have two diagrams. On the left here we have a diagram where we see that by changing the solar irradiation, the maximum power point of the PV array will shift, and the maximum power point here is represented with P max. So because this there will be this shift, we need to make sure that this point is being tracked at all times. And on my right here we see that how the maximum power point in the output characteristics PV curve of a PV array will correspond to a voltage which we say as the VMPP and a current which we say as the IMPP, and if and only if the panel is set at this voltage level and this current level, it will output its maximum power. Talking about the ripple correlation control, this is the algorithm that we have used for the controller. Here we see that we see two diagrams on the left and on the right, which is showing the panel voltage, panel power, and in the middle the inductor current from the converter. And we see that the inductor current and the power on the left is in phase, and on the right it is out of phase, or there's a phase difference of 180 degrees. So using these two, by correlating these, the inductor current and the panel power, we can actually find the maximum power point, since to the left of the maximum power point these two are in phase, and to the right these two are out of phase. This can be further properly understood on this slide here, and on this diagram we have divided the region as region 1 and region 2, where in region 1 to the left of the maximum power point we know that, as we have seen in the previous slide, these two, the panel power and the inductor current, are in phase, and in region 2 they are out of phase. So using this property, we can actually formulate a control law where if we take the derivative of the inductor current and the derivative of the power and find the product of those two derivatives, we see that it is greater than 0 in region 1 and it is less than 0 in region 2. It can further be formulated into a control law where we can extract a duty ratio out of it, which can be used to control the converter, as shown over here. Now let's talk about the advantages of using RCC. As we have seen that it does not require any external or artificial perturbations, rather it uses the inherent ripples of voltage and inductor current which are already present in the switching power converter, and it also does not rely on any assumptions or characterizations made on the PV array. It can be implemented by using digital microcontrollers, and it is a well-established algorithm, and it can track the rapidly changing maximum power point at a very fast tracking rate. Moving on, let's talk about the buck boost power converter prototype that was developed for this project. So here we have a 4-switch synchronous buck boost converter that was selected to accommodate the wide fluctuations in the array voltage that was observed throughout the course of emission. So by simply using a buck or a boost, it was not possible to accommodate all the wide fluctuations in the array voltage, because at certain points we needed to increase the output voltage or decrease it. This converter was designed using commercially available GaN transistors, and the reason for using GaN transistors was we could switch the converter at very high frequencies with a minimal loss. So that's the advantage of using GaN, and these GaN transistors were tested by NASA JPL to be radiation hardened, so they are already built for space use. And on this slide we see some charts where the converter parameters and design values are given, and as on the top right we have an efficiency versus output power graph. The blue line shows the efficiency versus output power of this prototype buck boost converter, and the gray line shows the output efficiency graph of the previous state-of-the-art converter. So we can clearly see that this one is working at a higher efficiency. Let's talk about some numbers where we found that it has the system has achieved an improved specific power greater than 1 kilowatt per kg and a power density greater than 2 watts per centimeter cube relative to the existing power converter for space application, and it has achieved a 5% peak efficiency improvement that was observed with an output current greater than 1 amp. So basically this converter prototype has been proven, it has shown that it can be by using GaN transistors, the higher power density could be achieved. Now let's talk about the simulation of this whole MPPT system in Sabre. So we have selected a PV array in 2x2 series parallel configuration, and To prove that the RCC algorithm is able to track the maximum power point at dynamic conditions, and a change in solar irradiation was injected at 75 milliseconds, where it was changed from 450 watts per meter squared to 900 watts per meter squared in mid simulation at 75 milliseconds. So this change was injected to see if the controller will be successful to track the changed maximum power point. This is the PV power and current graphs showing the different curves at 450 and 900 watts per meter squared, where we see that at 450 watts per meter squared the maximum power point is at around 1.5 amps and 100 watts, and at 3.2 amps and 205 watts corresponds to the maximum power point the panel outputs at 900 watts per meter squared. This is the overall diagram of the whole MPPT system, where we have the 4-switch synchronous buck boost converter, and all 4 switches are being controlled by a digital maximum power point controller, which is using the ripple correlation control algorithm, and it is taking in input signals in the form of the PV current, the PV voltage to calculate the PV power, and the inductor current. So it will use the RCC algorithm to correlate these the PV power and the inductor current of the converter, and then drive the converter to the maximum power point of the PV array. So the controller was designed by using the state AMS tool in SaberRD, and on the left we have the RCC algorithm. The state AMS tool uses state diagrams, and it can take in continuous input functions and use mathematical operators on them. And this is how we have designed the RCC algorithm, where the ripples in the panel power and from the inductor current will be correlated, and if there is a phase difference between them, then the duty cycle is decreased, and if there is not, then it is increased. So on the right here we have the PWM driving signal generation, which continuously drives the 4 switches in the converter, and the duty ratio of this driving signal is dependent on the RCC loop on the left here, which keeps on running iteratively and finds out the duty ratio at which can converge it to the maximum power point. We see the output curves of the converter. Here we have the panel power at the top, we have the panel current in the middle, and the panel voltage at the bottom. And the output shows that at 75 milliseconds we see that the panel power has actually jumped from 100 to 205 watts, as exactly shown by the characteristic curve, and the panel current as well has jumped from 1.5 to 3.2 amps. We see that more clearly over here, where we can directly correlate these two graphs side by side, where the maximum power of 205 watts at 3.2 amps is represented by the lines after 75 milliseconds, and the maximum power for 450 watts per meter squared at 1.5 amp and 100 watts is represented by the lines of this output curve before 75 milliseconds. So let's finish up with some concluding remarks and future works. So this paper has shown that RCC is an excellent MPPT method, and it works in dynamic deep space environments. By using GaN transistors and higher switching frequencies, we could achieve high power density, and the digital controller used here could effectively track the PV array MPP. And for future work, we will explore on different modifications and adaptations of the algorithm. So these were the references used. So thank you everyone. If there are questions, I can take the questions you can send me the questions in email.